Science Magazine presents a special issue each year on the scientific breakthrough of the year. In 2009, it's Ardipithecus ramidus, the most detailed look at early hominid life.
This is indeed a major breakthrough because this is something that even as scientists, we never expected. So we're sharing this new data to the general public, and it couldn't be more interesting than this.
In October, Science Magazine held a press conference with 4 of the 47 authors who, together, published 11 papers in the October 2nd issue of Science.
It is one of the most revealing hominid fossils I could ever have imagined, much less had the privilege of studying. If you were to ask someone on the street today, what did an early ancestor of humans look like? They would probably say, well, it would look like Lucy, and before that it would look like a chimpanzee. What the fossils that are being described in science today will tell you is that both of those conclusions are very incorrect.
So instead of thinking of something in between a chimp and a human, we have to think of this as really not a series of links in a chain as much as branches in a tree. And our branch is a very peculiar branch. We have very strange feet and huge brains. How did that happen? Well, we have to work our way back down our branch. And so we're getting pretty close to the fork that was between the line that led off to the chimpanzees and the line that led off to us. And Ardipithecus takes us pretty far back toward that branch and informs us that the node point, the junction, the last common ancestor, was neither human nor a chimpanzee. It was something entirely different.
It's living on the ground, walking upright, like us, spending a lot of time walking upright. If you saw it walk by, the walk would look a lot like ours, but it can't run like us.
The skeleton that we have is estimated to be around 4 feet tall and to weigh around 100, 110 pounds. And so that's why skeletons are important. They allow you to get at things like stature, limb proportions, and all of that. And I think one of the things that we would be most impressed by seeing Ardipithecus in the flesh would be the very small size of her face and brain case, the very large size of her arms and hands, and this grasping ability of her feet. She had a foot with an opposable large toe. It's the first time we've ever seen this in a fossil hominid. All the rest of them, even the Lucy species, fairly early at 3.7 to 3.2, and even with footprints, in the footprints, the large toe is right in line with the other toes. There's already an arch to the foot. Artie's foot was not like that. When Artie walked, it toed off of the lateral 4 digits, and the large toe was off to the side, acting more in stabilization instead of in toe off. And so it's a very different creature. What that does, what the maintenance of that grasping foot does for you, is to open up the arboreal environment.
So during the ramidus time, certainly the area was kind of aerial with major streams flowing from the highlands. This was already a basin, a valley. And so there were major streams, riverine forests, and canopy forests, wet. We can say this because we see a lot of sediments there, the sediments that were brought by these rivers, apart from the different animals that existed there. So geologically, we can see the environment was very conducive for those animals to live in.
That's how science proceeds. We make hypotheses, we test them with data, and sometimes they fail. And the hypothesis that the earliest bipeds evolved in a savanna habitat has now failed in the face of this new evidence.
Well, Ardipithecus ramidus' hands and forearms weren't as stiff as a modern chimpanzee or gorillas. If you're knuckle walking, going like this, you need to have a very stiff wrist, and you need to have fingers that can handle that weight and all the forces. And there's all sorts of adaptations that Ardipithecus did not have. It had a much more flexible hand and wrist, so it was able to free up the hands to do other things.
So it turns out that that last common ancestor was probably not a knuckle walker at all. Knuckle walking evolved independently in gorillas and in chimps.
More primitive morphological characters and systems have been retained, and as a consequence, even the human hand today is probably more primitive than the chimpanzee hand is today.
And that's really one of the biggest lessons of Ardipithecus, is that we can't just take a modern animal like a chimp or a gorilla and use it as a proxy for the last common ancestor. Chimps and gorillas have been evolving for 6 and 7 million years too. And so what we're seeing here is something that we never could have predicted from either a modern human or a modern chimpanzee. The only way to learn about this creature is through the paleontological record.
If we were a couple of chimps sitting here talking about our ancestor, we'd have very little to say, because there's almost no fossil record of chimpanzees, and there was none, in fact, until a few years ago. We now have a handful of teeth from about 500,000, which are very interesting, but they don't tell us a whole lot about the whole evolution of chimpanzees. There are no fossil gorillas either. And so if we knew these lineages, we'd know a lot more about ourselves as well. And partly because of this, it's been assumed that the last common ancestor of humans and chimps was rather chimp-like. And you can't deny it because you have no evidence that chimps were any different then than they are now. The significance of this is that it's earlier in time, nearer the last common ancestor. And if we want to know what the last common ancestor was and to try and understand the forces that led to our divergence from a chimpanzee ancestor, this is much more relevant.
We began to work in the Middle Awash in 1981. We really didn't know what was going to be found. This is a long-term, protracted scientific research endeavor. And this kind of work does actually take decades. It doesn't take that long if you don't find anything, but we've found a great deal. We've found something like 15 separate horizons in this kilometer of rock that have yielded hominid fossils. We have over 18,000 vertebrate fossils, thousands of artifacts from multiple horizons. Ardipithecus is one snapshot within that depository. But it's the best snapshot, and it's the most detailed snapshot. It is the most data-rich snapshot.
There are so few skeletons of fossil humans. There's, I don't know, 4 or 5. And you can tell so much more when you've got a whole skeleton than when you've got a few bits and pieces. Even if you've got bits of different parts of the skeleton, knowing that they're all associated in one individual is really exciting. The interpretations that go along with it are very provoking. Some of them are undoubtedly true, I'm sure. Others will be topics of discussion for a good while. But the basic data, I think, is what really counts here. And the fact that you've got a fairly complete skeleton, you've got a lot of other associated things, is what's, at this particular time period, is what's really significant about this specimen.
We may have thought that human evolution began somewhat by accident 1 million years ago with the discovery of tools, or 2.5 million years ago with the discovery of the first stone tools. But in fact, Ardipithecus tells us that we as humans have been evolving toward what we are today for at least 6 million years.
The name Ardipithecus ramidus is based on an Afar name for ground, Ardi, and ramid for root. And so if you want to think of it that way, it's kind of like the root of the ground apes. We in the Middle Awash Project try to respect the local culture by naming, when we can, the scientific name based on an Afar root.
Science is published by AAAS, the Science Society.